What if a transformer could grow new kinds of attention patterns without adding layers? Pretraining were really a form of compression, and a model could begin to behave like a computer with its own latent runtime. In today's episode, we connect 3 striking papers that push AI in very different directions: more expressive attention, a new information-theoretic view of learning, and the first steps toward neural computers. Together, they hint at a future where models think, remember, and act in far richer ways. Let's explore the first paper, Interleaved Head Attention. Interleaved Head Attention, IHA, targets a core bottleneck of standard multi-head attention. H-heads yield exactly H-independent attention matrices, so a single layer cannot jointly express multiple compositional relation patterns without adding heads or depth. IHA removes this isolation by learning P pseudoqueries, pseudokeys, and pseudo-values per head as linear combinations across the original H heads, then running standard scale dot product attention on the interleaved pseudotoken sequence. This induces up to P squared attention patterns per head while keeping the operator compatible with flash attention and rope. Parameter overhead is only OH squared P versus the linear head-by-head scaling of vanilla MHA. The paper proves a strict expressivity separation. MHA is a subset of IHA for any P is greater than or equal to 1, and strictly contained for P is greater than or equal to 2. On synthetic proxies for multi-step reasoning, IHA achieves asymptotic gains. On polynomial filters, it reduces required heads from k to second square root k, with parameter complexity theta square root kn squared w instead of theta nn squared. And on CPM3, it reduces one layer head count from mmax to square root mmax, with attention cost dropping from theta mmax cubed to theta mmax 2.5. Empirically, under flop match training of a 2 or B parameter decoder only transformer, IHA improves ruler multi-key retrieval by 10 to 20% at 4K 16K context lengths and raises overall ruler EM to 44% versus 40.6% for global plus local and 35% for global attention. After OpenThought's fine-tuning, it reaches 54.2%. GSM AK Maj at 16 and 18.4%. Math 500 Maj at 16, outperforming full attention by 5.8 and 2.8 points, respectively. On synthetic binary and ternary relation composition, IHA also beats MHA and simplicial attention by up to 4.7% and 3.3%. Let's explore the second paper, Learning is for Getting Learn, Training as Lossy Compression. This paper reframes LLM pre-training as lossy compression and tests that claim on open weight models using an information bottleneck analysis of hidden states. With a scalable soft entropy estimator, the authors estimate mutual information between representations and inputs. Output labels on 10,000 samples from C4 and Tulu, avoiding intractable clustering or binning at LLM scale. On OOMO2, pre-training follows the predicted two-phase trajectory. First, expansion in expressivity, then compression of input information as next token loss saturates, with models moving toward the IB frontier. This pattern holds across token, bigram, trigram, and quadgram backoff, and across model families including OLMO2, SMOLM2, Pythia, Llama, Gemma, Quen, and Aya command. Scale matters. OMO 27B and 32B approach optimal compression, while 1B often fails to reach the frontier and oscillates off-bound late in training. Across 47 open weight models and 6 benchmarks, MMLU Pro, BBH, Math Level 5, IFE Eval, GPQA, and Musser, the key predictor is not raw expressivity, but compression optimality, defined as I, Y, Z, I, X, Z. Lower token complexity correlates with higher performance. R equals minus 0.38, P equals 0.006, and optimality correlates more strongly. R equals 0.52, P, nicht zählig nicht Anna. The amount of preference information measured via IZ, preferred on Tulu preference pairs, is an even stronger predictor of downstream performance. R equals 0.76, P equals 0.001, especially for instruction following. The main substantive claim is that LLMs do not merely memorize. They converge toward different near-optimal compressions of training data, and the information that survives compression predicts behavior. Let's explore the third paper, Neural Computers. Neurocomputers proposes a new machine form in which a single learned latent runtime state, rather than an external operating system, unifies computation, memory, and I/O. The paper operationalizes this abstraction with two video model prototypes built on WAN2. One, NCC LIGen for terminal interfaces and NC GUI for desktop GUIs. Both are trained only from synchronized I/O traces, not instrumented program state. CLI Gen General uses 823,989 cinema-derived clips, about 1,100 hours at 15 frames per second, while CLI Gen Clean adds roughly 250K scripted VHS runs, retaining about 128K after filtering. GUI World combines approximately 1,400 hours of random interaction plus 110 hours of supervised Claude CUA traces in an Ubuntu 22.04 XFCE4 environment. The key technical result is that early runtime primitives are learnable. In CLI Gen, the reconstructed terminal frames reach 40.77 decibels PSNR and 0.989 SSIM at 13px font size. OCR character accuracy rises from 0.03 to 0.54 after 60K steps, and exact line accuracy reaches 0.31. Detailed captions improve PSNR from 21.9 to 26.89 decibels, showing that literal text-to-pixel alignment is a dominant control channel. However, arithmetic probes expose severe symbolic weakness. NCC LIGen scores 4% accuracy compared with 0% for the base WAN2 1 model and 2% for Veo 3 1. Reprompting alone raises this to 83%, implying that conditioning, not native arithmetic, drives most gains. For GUI World, action quality and supervision dominate scale. Goal-directed Claude CUA traces outperform much larger random exploration, improving global FVD from 149.61 to 14.72, and SSIM from 0.496 to 0.885. Explicit SVG cursor supervision is decisive. Position-only cursor modeling gives 8.7% accuracy. Fourier features 13.5%, but masked cursor references raise accuracy to 98.7%. Among action injection schemes, internal cross-attention performs best, reaching SSIM plus 15 of 0.863 and FVD plus 514.5. The paper's central claim is that NCs already exhibit I/O alignment and short horizon control, but durable reuse, symbolic stability, and explicit runtime governance remain unsolved. That's a wrap on today's AI paper highlights. Thanks for watching.